Right now, you're reading numbers that traveled over 1,000 years and thousands of miles to reach you. The digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 didn't originate in Europe, despite being called Arabic numerals. They didn't even originate in the Arab world, though Arabic scholars transmitted them westward. These numbers came from ancient India, where mathematicians created the decimal place value system that now dominates global mathematics. Every calculation you perform, every price tag you read, every phone number you dial uses a number system. Invented by Indian mathematicians between the 3rd and 7th centuries CE, this system was so revolutionary, so elegant, so powerful that it replaced every other number system it encountered. Roman numerals, Egyptian hieratic numerals, Greek alphabetic numbers all fell before the Indian decimal system, and at the heart of this revolution stood one man, Aryabhata, the mathematician astronomer who in 476 CE wrote a treatise that would change mathematics forever. Welcome to Math's Whisperer, where we uncover the hidden stories of mathematics. I'm your host, and this is Season 2, Episode 6. Today, we're traveling to ancient India to discover how one civilization gave humanity the most important mathematical tool ever created and why this gift deserves far more recognition than treatises. The story begins in the Gupta Empire, the golden age of Indian mathematics, science, and culture. Between 320 and 550 CE, while Europe was entering its dark ages, India was experiencing an intellectual renaissance. Universities flourished at Nalanda and Takshashila. Astronomers tracked planetary motions. Mathematicians developed sophistication, algebra and trigonometry. And somewhere in this fertile intellectual climate, the decimal place value system emerged. We don't know exactly who invented it. Mathematical knowledge in ancient India was often collaborative, passed between scholars, refined over generations. But we can trace its development through key figures and texts. The earliest traces appear in texts from around 200 to 300 CE, where we see glimmers of place value thinking. But it's with Aryabhata in 476 CE that we get our clearest early exposition of advanced mathematics using this system. Aryabhata was born in 476 CE, the same year the Western Roman Empire officially fell. While Europe was fragmenting politically and intellectually, Aryabhata was writing the Aryabhatiya, a mathematical and astronomical masterpiece that would influence Indian mathematics for over 1,000 years. The Aryabhatiya is compact, just 118 verses written in Sanskrit poetic meter. But within these verses, Aryabhata packed an extraordinary amount of mathematical knowledge. He covered arithmetic, algebra, trigonometry, and astronomy, and he did it all using the decimal place value system. Let me explain what makes this system revolutionary. Because we take it so completely for granted that we forget how brilliant it is. Imagine trying to multiply 47 times 80 to using Roman numerals. That's XLVII times LXXXII. How would you even start? Roman numerals have no place value. An X always means 10, regardless of where it appears. There's no way to efficiently perform multiplication or division. Now try it with Indian decimal numerals. 47 times 82. You can use the standard algorithm we all learned in school. Multiply 7 times 2, write 14, carry the 1. Multiply 7 times 8, add the carried 1. And so on. Simple, systematic, teachable to children. This is the power of place value. The same digit means different things depending on its position. In 333, the first 3 means 300, the second means 30, the third means 3. Position determines magnitude, but place value alone isn't enough. You also need a complete set of single-digit symbols, and crucially, you need 0. The Indian decimal system provided all of this. 9 symbols for 1 through 9, plus the revolutionary 0, and a clear positional notation where digits to the left represent larger values. With this system, you can write any number, no matter how large, using just 10 symbols. And you can perform arithmetic operations using standardized algorithms that work every time. Aryabhata used this system throughout the Aryabhatiya. He calculated square roots and cube roots. He worked with large numbers describing astronomical distances. He solved algebraic equations, all using the decimal place value system. But Aryabhata's contributions went far beyond just using the system. He developed sophisticated mathematical methods that showcased its power in algebra. Aryabhata solved linear equations and provided methods for solving certain types of indeterminate equations with multiple possible solutions. This work laid groundwork for later Indian mathematicians like Brahmagupta and Bhaskara, who would develop algebra to extraordinary levels. In trigonometry, Aryabhata created the first sine tables. He understood sine as a function, not just as a geometric ratio. He calculated sine values with remarkable accuracy, creating tables that astronomers and mathematicians would use for centuries. He calculated pi2 for decimal places, 3.1416. His method involved approximating a circle with polygons, similar to the technique used by Archimedes and Liu Hui. But Aryabhata's result was extremely accurate for the 5th century. In astronomy, Aryabhata made revolutionary claims. He stated that the Earth rotates on its axis, explaining the apparent motion of the stars. This was over 1,000 years before Copernicus proposed heliocentrism in Europe. While Aryabhata didn't go as far as placing the sun at the center of the solar system, his recognition of Earth's rotation was remarkably advanced. He calculated the length of the solar year as 365.25858 days accurate to within minutes of the true value. He explained eclipses correctly as shadows cast by celestial bodies, not as supernatural events. He calculated the orbits of planets with impressive precision. All of this required sophisticated mathematics. And all of it was made possible by the decimal place value system that allowed him to work with large numbers, perform complex calculations, and express results precisely. But Aryabhata wasn't working in isolation. He was part of a broader Indian mathematical tradition that continued to develop after him. Brahmagupta, who lived about a century after Aryabhata, 598 to 668 CE, made even more explicit contributions to the decimal system and to algebra. His work Brahmagupta, written in 628 CE, contains the first clear arithmetic rules for 0. Brahmagupta explained, when 0 is added to a number or subtracted from a number, the number remains unchanged. When 0 is multiplied by any number, the result is 0. He gave rules for dealing with positive and negative numbers, which he called fortunes and debts. He couldn't fully resolve division by 0. Nobody could until much later. And it remains problematic. But he established the arithmetic of 0 as firmly as anyone had up to that point. Brahmagupta also made major advances in algebra. He solved quadratic equations generally, providing systematic methods that would later influence Islamic and European mathematics. He worked extensively with indeterminate equations, developing methods that anticipated techniques Western mathematics wouldn't discover for centuries. After Brahmagupta came other brilliant Indian mathematicians, Bhaskara, the first in the 7th century, Mahavira in the 9th century, and Bhaskara the second in the 12th century, who wrote works that summarized and extended the entire Indian mathematical tradition. Bhaskara the second's Aryabhatiya, a mathematical textbook written in 1150 CE, covered arithmetic, algebra, geometry, and morale using the decimal system. It was written in beautiful Sanskrit verse and was so popular it was translated into Persian and used throughout the Islamic world and eventually in Europe. Throughout this entire period, spanning roughly 400 to 1200 CE, Indian mathematics was arguably the most advanced in the world. While Europe was using abacuses and Roman numerals, India had a complete decimal system, sophisticated algebra, and advanced astronomy. So how did this knowledge spread to the rest of the world? The transmission happened primarily through the Islamic world. During the 8th and 9th centuries CE, the Islamic Golden Age was in full bloom. The Abbasid Caliphate, centered in Baghdad, became a hub of learning. Scholars translated texts from Greek, Sanskrit, Persian, and other languages into Arabic. Indian mathematical texts, including works based on Aryabhata and Brahmagupta, were translated into Arabic. Islamic mathematicians recognized the power of the Indian decimal system immediately and adopted it. Al-Khwarizmi's name gave us the word algorithm, and the Indian numerals he popularized became known in Europe as Arabic numerals. Not because Arabs invented them, but because Europeans learned about them through Arabic sources. The system spread westward from Baghdad to Al-Andalus, Islamic Spain, and North Africa. From there, it gradually entered Christian Europe through trade, scholarship, and cultural exchange. One crucial moment came in 1202 CE, when Leonardo of Pisa, known as Fibonacci, published Liber Abaci, the Book of Calculation. Fibonacci had traveled extensively in North Africa and learned the Indian Arabic decimal system. His book introduced it to Europe, demonstrating its superiority over Roman numerals for commerce and calculation. But European adoption wasn't immediate or easy. Many merchants and scholars resisted the new system. They were comfortable with Roman numerals and abacuses. The decimal system seemed foreign, unfamiliar, even suspicious. Some cities banned its use, fearing that the new numerals would make fraud easier in financial documents. Gradually, though, the advantages became undeniable. By the 15th century, the decimal system was spreading across Europe. By the 16th century, it dominated. And by the 17th century, when modern science was emerging, the Indian decimal system was universal among European mathematicians and scientists. Imagine if this hadn't happened. Imagine trying to do calculus with Roman numerals. Imagine Newton writing the Principia Mathematica without the decimal system. Imagine modern physics, engineering, or computer science using any other notation. It would be impossible. The scientific revolution depended fundamentally on the Indian decimal system. The entire structure of modern mathematics rests on this foundation laid by Indian mathematicians over 1500 years ago. Yet this contribution is often underappreciated or misattributed. We call them Arabic numerals when they're Indian. Textbooks often skip from Greek mathematics directly to European mathematics, as if nothing important happened in between. Aryabhata, Brahmagupta, and Bhaskara are far less famous than Euclid, Archimedes, or Newton, despite making contributions of equal importance. This reflects a broader problem in how we teach history. Eurocentric bias that privileges Western achievements while marginalizing or ignoring contributions from other civilizations. The truth is that mathematics is global. Every major civilization developed mathematical knowledge. India's contribution, the decimal place value system, is arguably the single most important invention in mathematical history. It's the tool that makes all other mathematics accessible. Think about what the decimal system enables. Elementary school children can learn to add, subtract, multiply, and divide using standardized algorithms. Before the decimal system, calculation required specialist training. Abacus masters spent years learning their craft. Roman numeral arithmetic was complex and error-prone. The decimal system democratized calculation. It made mathematics accessible to everyone, not just specialists. This accessibility enabled the scientific revolution, the industrial revolution, the digital revolution. Every technological advancement of the modern era rests on mathematical calculations made possible by the Indian decimal system. Beyond practical calculation, the decimal system enabled theoretical advances. Calculus requires working with infinitesimal quantities and limits impossible to express clearly without decimal notation. Complex numbers, matrices, abstract, algebra. These developments built on the foundation of decimal notation. Computer science and digital technology are literally built on the principles of place value positional notation, binary base 2. Notation is just the decimal system based in with a different base. The same principles apply. Indian mathematicians who developed place value thinking and based in laid the conceptual foundation for binary computation. Every time you use a computer, you're using ideas that trace back to ancient India. So why don't we learn this in school? Why isn't Aryabhata as famous as Pythagoras? Why don't students learn that the numbers they use every day are an Indian invention? Part of the answer is historical inertia. For centuries, Western education centered on Western history. The classical curriculum focused on Greece and Rome, then jumped to Renaissance Europe. Asia, Africa, and the Americas were treated as peripheral or primitive. This is changing, thankfully. Modern historians of mathematics recognize the global nature of mathematical development. Textbooks are improving, but we still have a long way to go. Teaching the true history of the decimal system isn't just about giving credit where it's due, though that matters. It's about showing students that mathematics belongs to all humanity. That brilliant innovations came from every corner of the world. That mathematical thinking isn't the exclusive property of any culture or civilization. When a student in India learns mathematics, they should know that their ancestors invented the number system they're using. When a student anywhere learns mathematics, they should understand they're using a tool gifted to the world by Indian mathematicians. This knowledge can inspire. It can challenge stereotypes. It can show that scientific thinking flourishes everywhere, when conditions allow. The Indian mathematical tradition didn't end with the decimal system either. Indian mathematicians continued making contributions through the medieval period and beyond. The Kerala school of mathematics and astronomy, which flourished from the 14th to 16th centuries CE, developed calculus-like techniques. Centuries before Newton and Leibniz, Madhava of Sangamagrama, working around 1400 CE, discovered infinite series expansions for trigonometric functions. He developed methods for calculating pi to extraordinary precision. His techniques anticipated calculus by over 200 years. These contributions were less well transmitted to Europe, so they didn't influence the European development of calculus, but they showed that Indian mathematical creativity continued long after Aryabhata, producing insights of profound depth. The story of Indian mathematics reminds us that knowledge is cumulative and collaborative. Aryabhata, built on work by earlier Indian mathematicians. Later mathematicians built on Aryabhata. Islamic scholars transmitted and extended Indian mathematics. European scholars eventually learned from Islamic sources and built further. Mathematics advances through exchange, translation, and building on others' work. No civilization has a monopoly on insight. The greatest advances often come from cross-cultural fertilization, when ideas from different traditions meet and synthesize. Today, mathematics is truly global. Mathematicians from every continent collaborate, publish together, and build on each other's work. The internet has accelerated this collaboration. Mathematical knowledge spreads instantly, worldwide. But we should remember and honor the historical contributions that made this possible. The Indian decimal system is the foundation. Everything else builds on it. So next time you write a number, think about the journey those digits took, from ancient India through the Islamic world to Europe and eventually worldwide. Think about Aryabhata calculating with these symbols in 476. Think about the centuries of refinement by Indian mathematicians. Think about Islamic scholars who recognized their value. Think about European merchants and scientists who finally adopted them. And remember that the most basic tool of mathematics, the thing we teach to children before anything else, is a gift from ancient India to the entire world. If you're fascinated by the global history of mathematics and how different civilizations built on each other's work, subscribe to Maths Whisperer. We're releasing daily episodes exploring mathematical thinking across cultures and time. Tomorrow, we're diving into the Islamic Golden Age to meet Al-Khwarizmi, the mathematician who gave us algebra and whose name gave us the word algorithm, and who served as the crucial bridge transmitting Indian and Greek mathematics to Europe. Hit subscribe, ring that bell, and comment. Did you know that Arabic numerals actually came from India? Let's keep exploring mathematics together, one whisper at a time.